Okay, we're starting in on Chapter 2, Part 3, and let's just get our minds working again and start with a practice problem. So in this problem, you're asked, how far can a bus travel in 8 hours at an average speed of 60 miles per hour? So again, I can't stress enough, you want to make your list. So you're asked for how far, so you know that's a distance. So we're looking for distance. You're given the time that the bus travels of 8 hours, and you're given an average speed of 60 miles per hour. Now you should look at these units and see, am I going to need to convert? Well, no, because my answer is going to be in miles because I'm given miles per hour, so hours will cancel, so I'm good, and miles is a unit of distance. So here again, you start with your basic formula. Speed is distance over time. And on your formula sheets that you're allowed to use for the exam, you can take that basic formula and you can have it solve for the different variables. That's going to save you time on the exam. So I just keep solving it for you because it gives you some extra practice in solving equations. Okay, so we are looking for how far, so we're looking for distance, so we're going to multiply both sides by t, and then we're going to cancel out t, and therefore our formula is going to be t times v equals d. So our distance is going to be v, which is 60 miles per hour, and I'm writing this way so you can see the units are going to cancel, times 8 hours. So notice the hours cancel. My final answer is going to be in miles, and that's going to give me 480 miles. Okay, let's go back to our PowerPoint and pick up where we left off, and that would be picking up with acceleration. So we can change velocity in one of three ways. First, we can increase the magnitude. So basically, you're speeding up. Secondly, you could decrease the magnitude. So car slowing down. Or thirdly, you could change the direction of the velocity vector. So you're basically making a turn in your car. So any of these three ways, independent of the other, you can actually change your velocity. When any of those changes happen, you're actually accelerating. So your faster your change, the greater the acceleration is going to be. So you can think of acceleration as simply the time rate of change of velocity. So with acceleration, you're actually measuring the change in velocity during a time period. So our formula is going to be average acceleration is the change in velocity divided by the change in time. We use a lowercase a for acceleration. Remember we said the triangle is delta, which represents change. So acceleration is going to be delta v over delta t. Okay? Or for the most part, you just say t. So when we have delta v, we're looking at that change. We want to take our final minus our initial. So it's always going to be final minus initial. You use the subscript of f for final, subscript of 0 or I for initial. So our units are going to be different. If you remember, our units of speed were meters per second. Well, now our units of acceleration are meters per second squared. And this is the way you normally write meters per second squared. Okay. Now, in physical science, we're going to limit ourselves to situations where we have a constant acceleration. So if you look at this picture, as your velocity increases, the distance that's traveled by that ball is going to increase with each second. So this is showing you an object with a constant downward acceleration of 9.8 meters per second squared. Okay, so notice with that constant acceleration of 9.8 meters per second squared, after 1 second, the speed is 9.8 meters per second squared. After 2 seconds, it's 9.8 meters per second squared times 2, and then so forth, as that object is falling down. Okay, now in this problem, we're told we have a race car starting from rest, accelerating uniformly along a straight track, reaching a speed of 90 kilometers per hour in 7 seconds, and you're asked to find the acceleration. Well, if our car is starting from rest, that initial has to be 0. It reaches a speed of 90 kilometers per hour, so that's got to be our final, and it does so in 7 seconds. Now remember, we said that acceleration units are meters per second. But notice I don't have meters per second. I have kilometers per hour. So I want to convert 90 kilometers per hour to meters per second. Okay? And in this example of conversion, they kind of did it all in one step. If you'd like to see it broken down in the way I typically like to convert, you write what you need to convert. So we have 90 kilometers per hour. Okay, we look at our conversion factor and we see we have 1,000 meters in 1 kilometer. In 1 hour, we have 60 minutes. And then in 1 minute, we have 60 seconds. So let's check our units. So our kilometers cancel, our hours cancel, and our minutes cancel. So the units we're left with are meters per second, which is going to give us 25 meters per second. I like to do it in this long way because I see my units canceling and I know what's going on. So we come back up to our formula and we see acceleration is final minus initial velocity divided by time. So we have 25 meters per second minus 0 divided by 7 seconds, which gives us an answer of 3.57 meters per second. Now, remember, any equation we have, we can rearrange it to solve for all the different variables. The acceleration equation is no different. So, acceleration equaling final minus initial velocity over time, we can rearrange this equation and we can solve for final velocity. Okay? We could also rearrange this equation and solve for initial velocity. Okay, let's do that. Let's solve it, rearrange it, and solve for initial velocity since we already have it rearranged for final. So if we start off with acceleration is Vf minus V0 over t, first thing we're going to do is multiply both sides by t, and then we have at equals Vf minus V0. And we don't want V0 to be negative, so we're going to add V0 to both sides. That V0 is going to cancel. So we have AT plus V0 equals VF. We want V0 by itself, so we have to subtract by AT. Subtract this side by AT. The AT's cancel. V0 equals VF minus AT. So now we can solve this. We can find from this basic acceleration equation, we can now find acceleration, we can find VF, and we can find V0. Okay, let's do another problem. So it tells us in the preceding example a car in the preceding example continues to accelerate at the same rate for 3 more seconds. What will be the magnitude of its velocity in meters per second at the end of the time? So we calculated our acceleration to be 3.57 meters per second. Okay. Meters per second squared. We're adding 3 more seconds. So remember, initially we had 7 seconds plus 3 seconds. It's going to give us a total time of 10 seconds. That's where I get this from. We started from rest. So they're asking you what is going to be basically the final velocity. So the equation that we just saw how that was rearranged. So we take VF equals V0, which is 0, plus AT, acceleration is 3.57 meters per second times 10 seconds, and we get a final speed of 35.7 meters per second. Okay, let's look at a couple of acceleration problems. Okay, well actually, you know what we're going to do? We're going to go ahead and stop part 3 right here, and we will pick up with part 4 doing our sample problems.